Specification for Foundation Fieldbus, Part 1. Features of Fieldbus. Foundation Fieldbus is a robust, two-way digital communication system specifically designed for real-time distributed control in industrial automation environments. It provides a standardized platform for process instrumentation and control systems to communicate over a single shielded twisted pair cable, delivering both power and digital signals. Unlike conventional 420 milliamp systems, Fieldbus enables multiple devices to operate on a single segment, reducing cabling, simplifying architecture, and enhancing diagnostic capabilities. One of the most prominent features of Foundation Fieldbus is its ability to allow multiple field devices, such as transmitters, actuators, and controllers, to communicate simultaneously on the same bus. Each device can transmit and receive messages using deterministic scheduled communication protocols. This eliminates the need for analog signal duplication and dedicated I/O wiring for every instrument, offering significant cost and space savings for complex installations. The technology operates based on a distributed control model. This means control logic can be executed directly within field devices themselves rather than being centralized at the host system. Function blocks reside within intelligent field devices, allowing loop control functions, e.g. PID, analog input, signal select, to be executed locally. This distributed intelligence greatly enhances system response time, reliability, and scalability. Fieldbus is engineered for high reliability and diagnostic depth. Devices can continuously report status, fault conditions, calibration drift, and process abnormalities, enabling predictive maintenance strategies. This improves plant uptime, reduces manual inspection routines, and supports a proactive asset management approach. Diagnostic information is available at both the device and segment level and can be integrated with plant asset management software. Each Fieldbus segment typically supports up to 32 devices and can extend up to 1,900 meters in length, depending on power and topology. Repeaters and segment couplers can be used to extend reach or isolate areas of the network. The bus is powered using isolated power supplies with terminators at each end to stabilize communication voltage levels. Intrinsically safe variants, such as FISCO and entity models, are available for hazardous area deployment. Time division multiple access (TDMA) is used to schedule communication between devices, ensuring deterministic operation critical for control functions. This predictable communication model allows for precise timing and eliminates network congestion or signal collisions. Control in the field (CIF) is made possible by the scheduled cyclic and acyclic communication framework built into the Fieldbus protocol stack. Foundation Fieldbus systems integrate seamlessly with distributed control systems DCS through Fieldbus Interface Modules, FIMs, or Host Communication Modules, HCMs. These interface points enable centralized engineering, diagnostics, and alarm management while allowing control to remain decentralized in the field layer. Device configuration, calibration, and diagnostics are performed from the control room using integrated software tools. The protocol provides enhanced security by isolating field communications from higher-level IT networks. This is done through physical segmentation, firewall integration at the host level, and strict communication rules on the bus itself. Each device is uniquely addressed and registered, minimizing risk of unauthorized device communication or network flooding. Finally, Foundation Fieldbus complies with international standards including IEC 61158 and IEC 61784. Devices and components are interoperable across manufacturers due to rigorous testing and registration by the Fieldcom group. This open architecture ensures long-term system flexibility, simplifies upgrades, and protects investment across the project lifecycle. Specification for Foundation Fieldbus Part 2. Fieldbus-ready field devices. Fieldbus-ready field devices are intelligent instruments designed with embedded digital communication capabilities, allowing direct participation in Foundation Fieldbus networks. These devices include transmitters, control valves, positioners, and analytical sensors, all equipped with digital processors and function blocks. Their internal architecture enables them not only to transmit process measurements, but also to execute control logic, report diagnostics, and maintain synchronized operations with the broader automation system. Each Fieldbus device must comply with Foundation Fieldbus function block architecture. At a minimum, all devices shall include the transducer block linking sensor actuator hardware with communication, and at least one input, output, or control function block. Devices such as pressure transmitters typically include analog input AI blocks, while control valves feature analog output AO or proportional integral derivative PID blocks. These blocks enable devices to perform real-time measurement, actuation, and closed-loop control directly on the segment. Device interoperability is a critical requirement. All Fieldbus-ready instruments must be registered with the FieldCom group and include a device description (DD) and capability file (CF). These files ensure consistent behavior across host systems, allow accurate graphical representation of device parameters, and support full engineering and diagnostics integration. Devices lacking DD-CF registration are not permitted for installation in the Fieldbus network. In addition to basic process variables, Fieldbus-ready devices provide extensive secondary information, such as status flags, calibration records, diagnostics, alarm limits, and device identification. These features support advanced functions like condition-based maintenance and automatic commissioning. Device diagnostics can identify sensor drift, plugged impulse lines, stiction in valves, and loop integrity issues, enabling early intervention and reduced downtime. All devices must support the Link Active Scheduler (LAS) protocol for scheduled communication and be capable of operating within the strict time cycles of deterministic TDMA networks. Devices must be capable of assuming basic device, link master, or LAS backup roles as appropriate for their configuration. This ensures that in the event of a primary LAS failure, another device can maintain network timing and control integrity. Electrical design of Fieldbus-ready devices must conform to IEC 61158-2 standards for signaling and power. Devices must have low quiescent current consumption, typically 15 to 20 milliamps, and support segment-powered operation without external power supply. Intrinsically safe variants must meet FISCO, entity, or FNICO standards for use in hazardous zones and be marked accordingly. Mechanical construction must be suitable for field deployment under harsh industrial conditions. Enclosures shall be IP65 or higher, with corrosion-resistant housings, terminal seals, and weatherproof connectors. Explosion-proof EXD, flame-proof, or intrinsically safe certifications must be available where applicable. Mounting accessories such as manifolds, brackets, and flanges must be compatible with Fieldbus bus couplers and junction boxes. All devices must support local and remote configuration using standard engineering tools such as Field Device Tool (FDT), Device Type Manager (DTM), or host DCS configuration suites. Basic configuration must also be accessible via handheld configurators using the Fieldbus protocol stack. Field calibration, zero span adjustment, and mode switching, manual, auto, out of service, must be supported through the digital interface. Suppliers of Fieldbus-ready devices shall provide full documentation including DD-CF files, wiring diagrams, power consumption data, hazardous area certifications, and integration guides. Devices shall be clearly tagged and addressable with physical and logical configuration parameters preloaded where possible to support streamlined commissioning and loop check procedures. Compliance with project-specific device selection criteria, including manufacturer consistency and spare interchangeability, must also be ensured. All the files uploaded by the user have been fully loaded. Searching won't provide additional information. Specification for Foundation Fieldbus, Part 3. Communication Model. The Foundation Fieldbus communication model is designed around a layered architecture to ensure structured, reliable, and deterministic communication across field-level devices in industrial automation environments. It aligns with the simplified Open Systems Interconnection (OSI) model, implementing three core layers: physical layer (PHL), data link layer (DLL), and application layer (APL). These layers collectively form the foundation for transmitting time-critical process data, device status, and system diagnostics over a single digital communication bus. At the base of the communication model, the physical layer is responsible for transmitting electrical signals over a twisted pair cable or fiber optic medium. It defines voltage levels, signal waveform, cable characteristics, and termination rules. Above this, the data link layer ensures medium access control, addressing, frame validation, and deterministic scheduling via a mechanism known as the Link Active Scheduler (LAS). This layer is crucial in preventing message collisions and managing both scheduled and unscheduled communication across the segment. The application layer of Foundation Fieldbus is split into two sublayers: the Fieldbus Access Sublayer, FAS, and the Fieldbus Message Specification, FMS. FAS maps services to the lower data link layer and defines the behavior of virtual communication relationships, VCRs. FMS encodes and decodes data exchange between user applications, managing objects such as function blocks, events, domains, and programs. This layering allows abstraction between network management and application behavior. A key concept in the communication model is the virtual communication relationship, VCR, which represents logical links between communicating devices or functions. VCRs ensure data is delivered reliably to the intended recipient, whether the model is client-server, bidirectional query response, publisher-subscriber one-to-many periodic updates, or source sync one-to-many event distribution. Each VCR is uniquely identified within a device and across the network using local indices and global data link addresses. Messages pass through the layers via protocol data units, PDUs. Each PDU includes both control information and data payload. As a message descends through the layers, additional protocol control information, PCI, is added to support functions such as addressing, timing, and integrity checks. At the destination, these headers are stripped layer by layer to expose the original data to the application. This encapsulation method ensures message integrity and synchronization from source to destination. The data link layer uses a token passing mechanism managed by the LAS to coordinate message transmission. The LAS determines when devices can transmit and ensures messages are exchanged according to strict timing schedules. This allows function blocks in different devices to operate in synchrony, a critical requirement for executing distributed control strategies across a segment. To maintain synchronization and enable reliable execution of control logic, the LAS issues scheduled compelled data CD messages and manages the macrocycle timing structure. Function blocks such as PID or AI depend on precise timing to execute algorithms in step with data availability. The LAS guarantees this synchronization across all devices by enforcing a segment-wide schedule and periodically broadcasting the network time. Foundation Fieldbus supports both deterministic and non-deterministic communication. Scheduled communication handles time-critical operations like function block exchanges, while unscheduled communication allows for device configuration, diagnostics, and alarms. The LAS dynamically balances both types by allocating token rotation slots and enforcing message priorities. Overall, the communication model of Foundation Fieldbus provides an elegant and deterministic framework that merges physical layer signaling with layered digital control. It supports real-time, distributed processing in demanding industrial environments while minimizing wiring complexity and enabling predictive maintenance through extensive device diagnostics and communication transparency.